All right, so hi everybody, welcome back. What we're doing today is starting a new chapter. That's chapter 9 of Giancoli. And the topic here is linear momentum and center of mass. So let's get into this. We'll start by defining momentum. What does momentum mean in physics? Well, conceptually, you can think of momentum as some sort of measure of how difficult it would be to bring an object to a stop. So the more momentum an object has, the more difficult it would be, the harder it would be to bring it to a stop. That's the idea. Now, specifically, we want to focus on something called linear momentum. Later on, we're going to define something called angular momentum, so we want to keep those two things straight. Right now, we're thinking of linear momentum. This is defined as the mass of an object times its velocity. Okay, so the equation we have is P. Lowercase p stands for linear momentum. We put a little arrow above it indicating it's a vector. And it's equal to the mass times the velocity, which again, the arrow above it indicates that we're dealing with some kind of vector. So the SI units of momentum are going to be kilograms, that's our unit of mass, times a meter per second, that's our unit of velocity. So kilograms times meters per second. Okay, so strictly speaking, this is the formula that you use to write down the momentum of a single object with a certain mass and a certain velocity. Oftentimes, though, you're going to be dealing with situations where you have a group of objects that are moving together, and you want to know the total momentum of that group of objects. So the way you handle this is you simply add the momentum vectors individually. So P total of some group of objects would be P1, the momentum of the first, plus P2, momentum of the second, plus P3, and then you just keep adding however many momentum vectors there are to add. That's the idea. So P1 would be M1, V1, P2 would be M2, V2, P3, M3, V3, and so on. Again, just add however many of those terms you need to add to account for all the objects. Now, momentum is a vector. So when you add momentum, you have to account for the fact that it's a vector. So it's not as simple as just adding numbers. When we do this addition, you have to remember how vector addition works. Okay, so we'll get into all of that. But first, let's just get a little practice using the formula for linear momentum. So P is equal to M times V. What I want you to do is just make a couple estimates. First, estimate the magnitude of your momentum when you are running at full speed. So in other words, just figure out what the mass times the velocity would be for you running at full speed, okay? And then estimate the magnitude of your car's momentum when you're driving down the highway. Again, product of mass and velocity for your car driving down the highway. So take a minute, pause the video, come up with these estimates, see what numbers you get, and then we'll go through it together. Okay, so we'll start with the definition of momentum. P is equal to M times V. And the magnitude of that momentum would just be mass times the magnitude of V. So this is just mass times speed, in other words. So we'll start with the case of a person running at full speed. So of course, this is going to vary from person to person because we all have different masses and we have different running speeds. But I'll just use my own mass, about 85 kilograms for this. And how can I think about the running speed? Well, the fastest person in the world, Usain Bolt, can run 100 meters in about 10 seconds. So roughly speaking, 10 meters per second is the fastest speed in the world. I'm going to say I can do like a little bit more than half of that. I don't know if this is true, but again, we're just doing an estimate. Let's say 6 meters per second, okay? So therefore, my momentum, if I was running at full speed, would be 85 kilograms times 6 meters per second. So this would work out to 510. Units are kilograms times meters per second, or since we're just looking for a rough estimate, it's about 500. Okay. Okay, so that's a reasonable estimate for the momentum of someone running at full speed. Now, for a car driving down the highway, again, it depends on what kind of car you have, how massive it is, and how fast you're driving, but we'll assume you're driving around the speed limit, 65 miles per hour, which is about 30 meters per second, okay, approximately. What's a reasonable mass for a car? Typical, let's say, mid-size sedan. You're probably looking somewhere in the neighborhood of 1,500 kilograms, okay? So the momentum, that would be 1,500 kilograms times 30 meters per second, giving you about 45,000 kilograms times meters per second, okay? So obviously, as we expect, the car has much more momentum. Okay, so the next thing to talk about is the relationship between linear momentum and force. So now that we've defined linear momentum and we know how to calculate it, it's important to talk about the fact that it's related to force in a really fundamental way. So here's what I mean by that. We already have seen Newton's second law. It's the famous equation F equals ma. What I want to show you here is that there's a different way to write Newton's second law, and it's actually more general than F equals ma. And it goes something like this. A more general form of Newton's second law is the net force, okay, the sum of all forces on the left side, is equal to dp dt. This is saying the derivative of momentum with respect to time. That's what this is. Okay, so the net force is the derivative with respect to time of momentum. So what I want to show you now is that if we write it this way, that's completely equivalent to F equals ma. So let's work this out. So the first thing to note is that when you see P in this equation, that's momentum, and the definition is m times v. So in other words, we have the net force is the derivative with respect to time of m times v. Okay, so what do I do with that derivative? How do I evaluate it? Well, basically I have a product of two terms, mass and velocity, and I want to take the derivative of this product of two terms. We're going to use the product rule for derivatives to do that. We have to apply the product rule. So this is how that works. First, you take the derivative of the first term, which would be dm dt, and then you multiply by v, the second term just left alone. Then you add to that the first term just left alone, which is m, times the derivative of the second term, which is dv dt. Okay, so that's how you apply the product rule to this formula. But the thing is, we have dm dt in this term right here. That's saying the derivative of mass with respect to time. Well, for the most part, when you're looking at an object moving around, its mass isn't changing. So in most cases, we don't expect mass to be changing. So what we can say is, if the mass is constant, then dm dt is equal to 0. So there is no change, there is no derivative. That's just equal to 0, which means the first term is equal to 0. So we have 0 times v plus m times dv dt. And then you should be looking at this last term where we have dv dt. This is the derivative of velocity with respect to time. Okay, what is the derivative of velocity with respect to time? Well, that's acceleration. That's the definition of acceleration. So what we get out of this is basically F equals ma all over again, right? Because the first term goes away. The second term is just mass times acceleration. So this says the net force is equal to the mass times the acceleration. So what I want you to take away from this is I can write Newton's second law as F equals dp dt like this, or I can write it as F equals ma like this, and they're completely equivalent, okay? Completely equivalent ways of thinking about it. Okay, so let's take this relationship between momentum and force and go a little bit further with it. So what we derived earlier was the fact that the net force acting on an object is equal to dp dt, so the derivative of momentum with respect to time. Now what we want to do is simplify that a little bit by just focusing on one direction of motion. Let's just focus on, let's say, the x direction. And so our equation says F sub x, that's the net force in the x direction, is equal to dpx dt, so the derivative of the x momentum with respect to time. That's how you want to think about that equation. Okay, so we can rearrange it by putting the dt on this side, so multiply through by dt, and now we have dpx, so a tiny little change in x momentum, that's what that says, is equal to fx, that's the force in the x direction, times dt, which is a little bit of time that passes. Okay, so when you see an equation like this, you should be thinking, since I have little infinitesimals on both sides, I could integrate both sides of the equation. And we'll have to integrate from the start to the end of whatever interaction we're talking about. So here, what I mean is, on the left side of the equation, we're going to integrate dpx, and we're going to take that from px initial, so the initial value of the x momentum, to px final, the final value of the x momentum. On the right side, we're integrating over time, so we're going to need time limits on this integral. We're going to go from t initial to t final, whatever those two times happen to be for the situation we're looking at. So the left side is pretty simple. That integrates just to px final minus px initial. That's how this integral works out. And the right side we'll leave alone. And by the way, if you're looking at a final minus an initial value, that's just the change in the linear momentum. That's the change in px. So I could write that as delta px on the left side equals the integral from t initial to t final of f of x dx. So in other words, if I want the change in momentum, what am I doing? I'm integrating the force over time, okay? Integrating the force over time to get the change in momentum, okay? Okay, so let's put that aside and then review something that I hope you've seen in a calculus course, which is how do you calculate the average value of a function? So the problem we're interested in here is, let's say we have a function f of x, and if we graph it, if we plot it out, it really can look like anything. I'm just drawing some sort of random curve here, but again, this is just some arbitrary function f of x. And I want to know what the average value is in some interval. So let's say between xa over here and xb over here. So of course, the function is changing all the time. It's going up and down, but there is some average value it has in that interval. So there's a way to calculate that average value. This is called the mean value theorem. And the way we do it is we calculate 1 over delta x, where delta x is just how big this interval is. So it's xb minus xa. That's the factor out front. And then we just integrate from xa to xb f of x dx. So you integrate over the integral, that function you have, and then you divide by the width of the interval delta x. That's how you get the average value of a function. That's how it works. So there's your delta x. That's the width of the interval down here. And the average value is some point on the vertical axis. Okay, let's say that's the average value. So if I rearrange what I just wrote down, okay, to solve for the integral, right? I just want to solve for this piece. Well, I'm just going to take delta x over to this side. Okay, so the integral of f of x between xa and xb is equal to the average value times delta x. Okay, so that's another way of thinking about that result. And actually, we can interpret that graphically because, of course, the integral of our function f of x dx integrated between xa and xb, that's the area under the curve. So that's what's shown in blue here. That's this area. But there's another area, if we look at the right-hand side of the equation, if we just look at f average times delta x, well, you can think of f average as this height right here that takes you to the average value. And again, delta x is this width right here. And together, when you multiply this height times this width, you have the area of a rectangle, and that's what's shown in red. So the point is, this blue area, okay, is equivalent to this red area. Those are the same thing. Okay, so I want us to take what we just learned by doing that little calculus detour and apply it to momentum and force, to apply it so we can understand the relationship between momentum and force a little better. So what I want you to think about now is the fact that when you have two objects interacting with each other, they're exerting forces on each other, but those forces don't have to be constant. Those forces might be changing in time in some way. So the way we would graph this out is if we had force on this axis and then time on this axis, the idea would be instead of just having some constant value for the force would be changing in some way. To give you a more concrete example, let's imagine you're throwing a ball at a wall and then it bounces off the wall, okay? So the moment that the ball makes contact with the wall, that's when you start to have a force. Before that, there is no force because they're not even in contact. And then as the ball begins to press into the wall, the force goes up. But then the ball begins to bounce back, force goes down, and then eventually the ball's not touching the wall anymore, and the force goes back down to zero, and then the ball just flies off. That's the kind of thing you might imagine is going on here. But in general, we just have some kind of force that's changing over time, okay? All right, so what we already learned is that the change in momentum is given by the integral of force over time. So in other words, delta px, we derived, is equal to the integral from t initial to t final of fx dt. So we're integrating this force over time to get a change in momentum, okay? What kind of change in momentum results from the force? So, well, since we're just integrating the force, that would be the area under the curve. That's how you would interpret this integral. So another way of saying the change in momentum delta px is it's the area under the force versus time curve. That's what's shown in blue. But of course, we can also express that integral as the average value of the function times the width of the time interval. Okay, so this is what we learned just a second ago in that little calculus review. So we have a time interval delta t. That's just how much time passes between t initial and t final. We have an average value. That's just whatever the average value of the force is in that time interval. And again, that product of those two, the f average times the delta t, you can interpret that as being this red rectangular area, which again, we know is equivalent to this blue area, which is why we're able to say that it's also equal to delta px. Okay, so a more useful way of thinking about delta px is it's the average force times the time interval. Okay, so we don't have to do this integral. Okay, so let's take a minute to step back and think about all the different results we derived. Okay, I want to kind of summarize everything. So first of all, a quantity that kept popping up was delta p, this change in momentum. So that's an important quantity. We should give it a name. Delta p is called the impulse. Okay, so delta p is the change in an object's momentum. That's called the impulse. That's the name of that quantity. And the way you calculate it is basically p final minus p initial. Okay? Now, think about intuitively what it would take to deliver an impulse to an object. Like, what would you have to do to change the momentum of an object? So an object is moving along, it has some mass, it has some velocity, and you're trying to change the momentum somehow. To do that, you're going to have to exert a force on the object, okay? And you're going to have to exert the force for some amount of time. Okay, you can exert the force for 5 minutes, you can exert the force for 2 seconds. You're exerting a force for some amount of time. That's the idea. Now, of course, the bigger the force you apply, the bigger the impulse, the more you will change the momentum of the object. But also, the longer you apply the force, the more impulse you'll get, the more you'll change the momentum of the object. And that's pretty much what the result we just derived said, okay? What we just derived is delta p is F average times delta T. Okay, really important result right here. And before we were just deriving this for the X direction, but you can apply this to the Y direction and the Z direction too. And in general, what you can say is the vector delta P is equal to the vector F average times delta T. So this is the general result, okay? And what it says is, on the left side, we have the impulse you deliver to an object. On the right side, we have the product of the average force acting on the object and the amount of time that force acts, okay? So this is kind of the fundamental relationship between momentum and force. Okay, so let's put that to use. Now that we've derived this important result, let's do a calculation with it. So we have a rubber ball with a mass of 275 grams, and it's moving horizontally this way with a speed of 12.5 meters per second. It hits this tilted wooden board, and immediately after hitting the board, it bounces off moving this way at 10.5 meters per second at an angle of 75 degrees from the horizontal. Okay, so a couple questions. What is the impulse that the board delivers to the ball? What is the change in momentum that the ball undergoes because it hits the board? And if the ball is in contact with the board for 74.5 milliseconds, that's how long they're touching down here, what is the average force exerted on the ball? So for each of these answers, we're going to give a magnitude and a direction. So let's work it out. Okay, so what we'll start with is the impulse. Let's calculate the impulse that's delivered to the ball. And remember, the definition of impulse, delta P, is P final minus P initial. So the initial momentum, P initial, would be the momentum of the ball over here just before it hits the board. And the final momentum would be over here just after it bounces off. And of course, momentum is defined as mass times velocity. So we would have mv final for the final momentum minus mv initial for the initial. Okay, so let's try to remember, generally speaking, how we subtract two vectors, because that's what we're doing here. The way we do it is we break each vector into x and y components, and then we subtract. So the first thing we need to do is break each of these vectors into x and y components. So if I have a velocity, let's say this is my velocity vector, okay? How do I break that into x and y components? Well, the vector will have some angle theta above the horizontal, which we can label there. And then Vx would be the part that points along the x-axis over here. And Vy would be the part that points along the y-axis over here. So it's really just a matter of remembering your sines and cosines. So sine of theta, if you remember, is opposite over hypotenuse. What's the opposite side here? Well, that's Vy. The hypotenuse is the magnitude of V, the speed. And Vy, therefore, is magnitude V sine theta. And what's the definition of cosine? Well, that's adjacent over hypotenuse. So the adjacent side in this right triangle here is Vx. The hypotenuse is just the magnitude of the velocity. That's the long side. So therefore Vx is magnitude V cosine theta. Okay, so that's how we'll break each vector into components. Okay, so the next thing we'll do is use those ideas I just outlined where m times V final can be written as the mass, and then V final would be the magnitude of V final, cosine of theta for the final velocity. That would be the x component. And for the y component, we would have the magnitude of V final times sine of that angle. So we'd put j hat for that. And then if I'm subtracting m times V initial, I'll have m. My initial velocity is magnitude V initial cosine of the initial angle That would be the x component. And then the y component would be the magnitude of the initial, sine of the initial angle. So I'd put j hat next to that because it's the y component. Okay. So actually, now we can just compute this, all right? So what I'm going to do to compute this difference between mv final and mv initial is just plug the numbers in. So what's the mass? I have 0.275 kilograms. Okay, so 275 grams is equivalent to 0.275 kilograms. And what's the magnitude of my final velocity? What's this? Well, that's how fast the ball is moving at the end, which is 10.5 meters per second. What's the angle? 75 degrees. Okay, so this would be the x component for that final velocity. 10.5 meters per second times cosine 75 degrees. The y component would be 10.5 meters per second sine 75 degrees. And then again, I'm subtracting, so I'll write this on the next line. Same mass, which is 0.275 kilograms. Now, what was my initial speed? What is the magnitude of the initial velocity? That's going to be 12.5 meters per second. That's how fast we're moving before we hit the board. And then here, what's the angle that I'm referring to for my initial velocity? That would be 0 degrees. It's just pointing directly along the x-axis, okay? So I'd have cosine 0 times I hat. And then I'd have 12.5 meters per second sine 0 times j hat. Okay, so this is what I need to calculate. And again, the idea here is just to keep track. I'm subtracting two vectors. So I'm going to get a vector as a result of this. It's going to have an x component and it's going to have a y component when I do this subtraction. If I want to think about what the x component works out to, this is what we're looking at right here. I'm just taking the first x component, which is 0.275 times 10.5 times cosine 75, and then I'm subtracting from that 0.275 times 12.5 times cosine 0. So that's something you can punch into your calculator, and you'll get minus 2.690. The units here are kilograms times meters per second. And we'd keep 3 sig figs on that. And we do the same thing for the y components. So just take the two y components that are shown in this column here and subtract one from the other. And don't forget that the mass is being multiplied out front. So we have 0.275 times 10.5 times sine of 75 degrees minus 0.275 out front here times 12.5 times sine of 0. So again, you can compute that, and you're going to get positive 2.789 kilograms meters per second. So that's delta P written in XY form. Remember, we did all this work to calculate delta P. So what would the magnitude then be of delta P? What is the magnitude of the impulse? Well, like any vector, if I take the square root of delta px squared plus delta py squared. That's the Pythagorean theorem, by the way. I can get the answer by plugging in these x and y components, which we just calculated. So I have minus 2.690 kilograms times meters per second for the x component. For the y component, I have 2.789 kilograms meters per second, and we'll square both of those, add them together, then take the square root. That's how we do this. And what you'll get is 3.874 kilograms times meters per second. Okay, but we'll keep 3 sig figs on that. So that's the magnitude of the impulse. Okay, what about the direction of the impulse? What direction is this vector going in that we found over here? Well, remember this. tangent of the angle of a vector is given by the y component over the x component. But let's actually take a close look at this vector here. Since x came out negative and y came out positive, we're in the second quadrant. Okay, so this vector is pointing in the second quadrant. So something like this in the second quadrant for delta p. So because of that, when I go to calculate the angle theta, of course I'm going to take the inverse tangent of delta py, which is 2.789, over delta px, which is negative 2.690. But I have to add 180 to that since we're in the second quadrant. Okay? So if you actually just calculate, tangent inverse, of that quantity, you'll get minus 46.04 degrees. And we'd want to round that to 3 sig figs right here. But again, I have to add 180 to correct for the fact that we're in the second quadrant. And this rounds off to 133.96 degrees. We'd want to keep that first decimal place there, so we'd write this as 134.0 degrees. Okay, so in other words, this delta p that we just showed is making an angle of about 134 degrees off the x-axis. That's what we just showed. Okay, so here, let's just write that in summary. The impulse is 3.87 kilograms meters per second at an angle of 134 degrees from the x-axis. That's what we can say about the impulse. Okay. So the hard part is over, because now that we know delta p, it has a very simple relationship to force, which is delta p is F average times delta t. So now we calculated the change in momentum, we can calculate the average force by simply taking delta p over delta t, just like that. So if I want to know the magnitude of the average force, I would just have to take the magnitude of delta p on the right side. So because we're interested in the magnitude of the force, that's what we'll do. So the magnitude of delta p on top is 3.874 kilograms times meters per second to 3 sig figs. Now delta t is the amount of time that passes. This is 74.5 milliseconds. A millisecond is 10 to the minus 3 seconds, okay? So that's delta t. How long is there contact between the ball and this wooden board? All right, so you go ahead and calculate this, and you'll find it comes out to 52.0 on the dot. And what about our units? We have kilograms, we have meters per second squared now, because we have two factors of seconds if you take a look at the previous calculation on the bottom. And this is equivalent to a Newton. Okay, so it's a force. Okay, so therefore the average force is 52 newtons. And what angle is that force applied at? The same angle we got before. 134.0 degrees from the x-axis. So I just want to make sure it makes intuitive sense that in order for the ball to bounce this way, we're saying the force is pointing in this direction, more or less. Okay, where the angle, again, from the x-axis here is 134 degrees. Hopefully it makes sense that the average force would have to be pointing in that direction in the second quadrant to make the ball bounce this way. Okay, so that's how you do this one. All right, so here's an example that I'd like you guys to try out. We have a 125 gram ball thrown at a wall, and it bounces off of it in the exact opposite direction. So the ball's coming in like this, moving towards the wall, collides head on with it, and then it bounces in the exact opposite direction back the other way. So let's suppose that the speed of the ball is 12 meters per second just before it hits the wall, and 12 meters per second just after. So it's moving at the same speed, it just turns around, okay? So if we suppose the ball is in contact with the wall for 12 milliseconds, what is the impulse? And what is the average force that the wall exerts on the ball? So try to figure these two out. Again, we're going to use the same formulas, but actually in this case, the geometry is a little bit simpler. So pause the video, see if you can get this, and then we'll go through it together. Okay, so let's take a look at this one. We'll start by calculating the impulse, which again is delta P, which is P final minus P initial. And of course, the initial momentum would be the momentum of the ball just before it hits the wall. And P final would be the final momentum after it bounces back the other way. So as usual, we can think of this as M times V final minus M times V initial. But the thing is, both V final and V initial only have an X component. There's no Y component to these velocities. So it's actually pretty simple to write down. What we have is, for M times V final, the mass is 0.125 kilograms, to convert that to kilograms. Now, what is V final? So we're moving in the negative X direction. So I want to put a negative sign on that final velocity for that reason. And we're moving with a speed of 12 meters per second. And if I bring along the I hat unit vector, that's how I show that we're moving at 12 meters per second in the negative X direction after bouncing off the wall. Okay, then I have to subtract from that the same mass, which is 0.125 kilograms, times times V initial. So the initial velocity, the ball is traveling in the positive X direction at 12 meters per second. So I'll write that as positive 12 meters per second I hat. So it's really important that you account for the sign difference between the two velocities. If you don't do that, you're gonna get this wrong. So you have to account for the difference in sign. But once you do that, what you're gonna find is this works out to negative 3.00 kilograms times meters per second I hat. So notice how the impulse delta P is pointing in the negative X direction. So it's pointing away from the wall. Okay, now we can do the average force, because of course delta P is given by F average times delta T. So we want to find F average. It's going to be delta P over delta T. Let's just directly plug in what we know. For the change in momentum, we have minus 3.00 kilograms times meters per second I hat. So that's how you write delta P in vector form. On the bottom, we have delta T, which is 12 milliseconds. Okay, so the idea is the ball is actually touching the wall for 12 milliseconds. 12 milliseconds is 12 times 10 to the minus 3 seconds. Okay, so compute that. You're going to get minus 250. It will work out exactly to minus 250. I want to keep 3 sig figs on that guy. And the units are kilograms times meters per second squared once again, so we know that's a Newton. And then we have the I hat unit vector floating here. So to summarize, we could write this as minus 250 or 2.50 10 to the 2 in scientific notation, newtons I hat. So there's your average force. Now, the direction of the average force is in the negative X direction. That's what this is showing us. So the average force is away from the wall. That should make intuitive sense, okay? If a ball comes in traveling to the right, and we want it to bounce off so that now it's going to the left, well, there's got to be a really big force pushing it to the left to make it bounce that way. And that's exactly what our answer is showing us. Okay, so that takes us to the next topic, which is conservation of momentum. Now, before we actually get there and we state what the law of conservation of momentum is, what it's all about, how to apply it, and things like this, we first have to set the stage. So the first thing to talk about is systems of particles. So if we really want to understand conservation of momentum, we're going to need to shift our thinking a little bit. So before, we were thinking about just single moving objects, like a box sliding across the table or something like that, just a single object to keep track of at any given time. Now we need to start thinking about systems of particles, meaning there are multiple objects to keep track of that are moving around. So this is pretty broad. An example of a system of particles could be an object, like a solid object. A baseball bat, for example, is basically just a huge collection of atoms that are all bound together. So certainly if you have a bunch of atoms moving around, that would be a system of particles. So any kind of like solid object is a good example of this. Also, you can have a bunch of independently moving objects. So a good example of this would be billiards. So if you have 15 different billiard balls colliding and moving around on a pool table, that would also be a system of particles. So the point is we have more than one thing to keep track of, okay? So if we say that this is our system of particles, we're keeping track of all of these red dots. Those are the particles we want to keep track of. I can draw a little boundary around that and say, that's my system. And in that system, we have different masses, potentially. So the first particle could have a different mass than the second particle. We can label those different masses as M1 and M2, and then all the way out to the last one, which is Mn. So n is just how many particles we have. Each one has a different position. So R1 would represent the position of my first particle, R2 is the position of my second one, and so on. They all have different velocities. So V1, V2, and so on would be a list of all the different velocities. And then they have potentially different accelerations. Okay, so that's the basic idea I want you to think about. The fact that we have multiple objects to keep track of. They could have different masses, different positions, different velocities, different accelerations. Okay, so that takes us to the difference between an internal force and an external force. So right off the bat, whenever you're dealing with a system of particles, you have multiple objects that you need to keep track of. It's always a good idea to start the problem by very clearly defining what your system is. And sometimes the way we do that is by drawing a little boundary, just an imaginary boundary, around the things that you're going to include in your system. So now it's very clear that anything inside of here is inside my system, and then anything outside of here is outside of my system. So you're actually free to choose the system however you want, right? I can draw this boundary however I want, but once I do that, I have to stick with my choice, okay? So I have to be clear on what I'm considering to be inside and what I'm considering to be outside of my system. And so once I've done that, now I can make a distinction between what's called an internal force and an external force. So this is pretty straightforward. An internal force is any force that's exerted between two objects in your system. So if we look at this picture at the bottom of the page, what's going on here? I've got a little board that these two people are standing on, and they're holding a rope. They're pulling on opposite ends of this rope. So if I'm defining my system to be this, okay, then the force of tension that they're pulling with would be an internal force, right? It's between two objects in my system. But let's say there's this guy outside of the system pulling both of them along with this rope. That would be an external force because it's coming from something outside of the system. Okay, so internal force is between two objects in the system, and then external forces are coming from something outside of the system. That's how that works. Okay, so with all of those new ideas in mind, what we're going to do is a little bit of a derivation. So I have some kind of system of particles. This can really be any kind of system of particles you can think of. So here's a couple of those particles. And we can draw a little boundary to say, that's my system. Okay, so for each one of those particles, we can say that the net force acting on the particle, well, we could say it's equal to mass times acceleration, but remember, we could also write this as dp dt. So I'm going to choose to write it as the derivative of momentum with respect to time. This is just Newton's second law. Okay. So what if we add all the forces acting on all the particles? So in other words, I would take the sum of the forces acting on particle number 1, and I would take the sum of the forces acting on particle number 2, and this would just be a big sum, right? I'd have to go complete this sum until I get to the last particle, which I'll call Fn. And on the other side of the equation, what are we going to have? Well, each one of these force terms is equal to dp dt. So I'll have dp dt for particle 1. I'll have dp dt for particle 2. And then this is a big sum all the way to the last particle, so dpn dt. Okay, that's what we're dealing with here. So on the left side, there are a whole bunch of forces. But broadly speaking, we can divide them into internal forces and external forces. Okay, so forces can be classified as internal or external. So in other words, when I have this huge sum of forces on the left-hand side of the equation, I can just write that as, look, I've got a bunch of internal forces, so add all of those up. And then I've got a bunch of external forces, add all of those up. Okay? So we're just putting everything into one of these two buckets. And on the other side, I have a bunch of derivatives, right? I have the derivative of the first momentum and the derivative of the second and so on. So I can actually pull out the derivative. This would be the derivative of P1 plus P2 plus ... Pn. That's what we have on the other side of the equation. Okay, so let's take a closer look at internal forces. So let's say, okay, this is particle number 1 over here, and this is particle number 2 over here. So if particle 1 and particle 2 are exerting forces on each other, that would be an internal force. So let's just pick 1 and 2 as an example. So here's number 1, here's number 2. Okay, so I don't know, maybe they're attracted to each other, just as an example. So that force that particle 2 exerts on particle number 1 would be pointing to the right like this, and then force that particle number 1 exerts on particle number 2 would be pointing to the left like this. Okay, that would be an example. But here's the thing, by Newton's third law, these two forces I just showed you are equal and opposite. Okay, that's really what Newton's third law says. So in other words, F21 is equal to negative F12. That's how I show the two forces are equal in terms of their size, but they're pointing in opposite directions, okay? But what happens if I add these two? Well, these obviously will add to 0, right? Because one is just the negative of the other. If I add them together, I get 0. So the point about internal forces is they all cancel each other out. They cancel in pairs like this, right? They all come in pairs, which just cancel each other out. So what we can say is the sum of internal forces is going to be 0. They're always just going to add to 0. Newton's third law ensures that's the case. So if we go back up here, where we have the sum of internal plus the sum of external forces, the internal forces are summing to 0. So then we're just left with F external, the sum of the external forces, equaling, I have the derivative with respect to time of P1 plus P2 plus ... plus Pn, adding up all these momentums. Well, that would just, we can think of that as the total momentum. So what does this say? The total external force on a system, that's what the left-hand side of the equation says, is equal to the derivative of the total momentum of the system with respect to time. Okay, so if we take this a step further, what if, so here, let's just say, suppose the net external force, the total outside force acting on your system, is equal to 0. Well, that will imply that dP dt is equal to 0 for your system. That means momentum, total momentum, is not changing. In other words, it's conserved. So that's where conservation of momentum comes from. All right, so you've seen the derivation, now you've seen where this comes from. So what I want you to take away from that is this result. First, we have this equation here, which says that the net external force, so you sum up, you add up all the external forces acting on a system, it's equal to dP dt, so the time rate of change of the total momentum of that system. And conceptually, what this equation is telling you is it's only outside forces, only external forces that can change the momentum of a system. Internal forces don't do that. And of course, if we imagine that there is no overall outside force acting on a system, so the sum of your external forces here goes to 0, well, that automatically implies that this side of the equation is 0 as well. So we have then, with no outside force, dP dt for your system is equal to 0. Again, that's just saying that the momentum is not changing over time. In other words, it's conserved. Right, but you can only use this idea of conservation of momentum when there is 0 external force acting on your system, okay? This is the only time it applies. Otherwise, momentum is not conserved, okay? So as long as you have a system where there's no outside force acting on it, then momentum is conserved. And the way we typically write this is just P initial is equal to P final, okay? So if we compare the system at some initial time and some final time, the total momentum is going to be the same at those two times. Okay, so before we get into any examples where we actually make calculations, I just really want to drive this point home that you really have to be careful about how you define your system before you try to apply conservation of momentum. So be really clear about what's in your system, what isn't, before you attempt to use conservation of momentum. Because again, conservation of momentum only applies when you're looking at a system where there's zero outside force acting on it in total. So to give you an example, just a really simple example to think about, let's imagine two pool balls colliding on a table. And to make it even simpler, let's just imagine there's no friction. Okay, so in the initial state, over here, we have the 12 ball moving to the right, and the 11 ball is just at rest on the table. So if you've played pool before, you may have noticed that if you align the shot just right, you can get it so that after the balls collide, the 12 ball just comes to a stop. That's just not moving. And now the 11 ball is just moving off to the right. So you might want to use conservation of momentum to sort of relate what's going on here to what's going on here, right? But again, if you're going to do that, you better be careful about how you define your system. So for example, let's say that I defined my system just to be the 11 ball. Okay, let's say I just drew a little box around this and said, that's my system. Well, obviously momentum is not conserved for that system, right? Because initially the 11 ball is not moving at all, so it has no momentum. But then after the balls collide, it does have some momentum. It's moving to the right. So momentum is not conserved. It's not staying the same. Well, the problem with choosing this as your system, of course, is there's an outside force, right? The 12 ball is an outside force that hits the 11 ball. But if you define your system to be both of those balls together, the 11 and the 12 ball together are your system, then momentum is conserved, okay? That's the kind of thing I'm talking about. So if we define the system, to go into more detail about this, if you define the system as the 12 ball and the 11 ball together, and we're kind of looking at them right when they collide, right when they're touching. And again, we're ignoring friction and air resistance. We're trying to make this as simple as possible. Let's just draw all the different forces that are acting on these balls. Well, you have the force of gravity, which is the weight. And I'm being a little fancy with my notation here. This says this is the weight that the Earth exerts on the 12 ball. That's just a downward force of gravity. Of course, the 11 ball is pushing on the 12 ball to the left when they touch. So that force I'll just call the force that the 11 ball exerts on the 12 ball going to the left like this. And of course, there's also a normal force. There's a table down here supporting the 12 ball. So it pushes up with a normal force, which we'll call N table on the 12 ball. Okay, so just to label the forces really carefully. Now, on the 11 ball, we have some forces too. We have the force of gravity. That's the weight that the Earth exerts on this ball. We have a normal force from the table, just like over here. And then also we have a force from the 12 ball. So the 11 ball is being pushed to the right by the 12 ball to indicate that we have a little arrow going off to the right, which we'll label F, that 12 exerts on 11. Okay, so those are all the forces in our system, right? Those are all the forces. And we'll notice that these two forces, okay, they're equal and opposite, right? The force that this ball exerts on this ball is equal and opposite the force that this ball exerts on this ball. That's basically Newton's third law, that those are equal and opposite forces. Okay, so the internal forces would be anything that's exerted between the two balls. So that would be these two forces here. Those would be considered internal forces, all right? External forces would be everything else because these two forces are being exerted by the table. The force of gravity is being exerted by the Earth. So these are outside of our system. These would be external forces. Okay, so what is the sum of external forces? I'd be adding up this normal force and this weight, and those two would just cancel each other out. Then I would be adding up this normal force and this weight, but those two would just cancel each other out. So the point is, since we have cancellation of all those forces, that the total outside force acting on our system is equal to 0. That's why we can use conservation of momentum, because the total outside force acting on the 11 and the 12 ball together is equal to 0, so momentum is conserved. So if we want to analyze what's going on when those balls collide, we can use conservation of momentum. Okay, so let's do an example just like that. We have two pucks, puck number 1, puck number 2, okay? They're sliding around on a level and perfectly frictionless air hockey table. So initially, puck number 1 over here is at rest, and puck number 2 is coming towards it at 2.45 meters per second. Then they collide head on. After this collision, puck number 2 is moving a little bit slower. It's moving to the right at a reduced speed of 1.05 meters per second. The question is, what is the final speed of puck 1? After they collide, how fast is puck number 1 moving off? The masses of the two pucks are given here. What I want you to do is use conservation of momentum to try to figure out how fast this one is moving off after they collide. So pause the video, see if you can work this out, and then come back to it and we'll go through it together. Okay, so start by defining what our system is going to be. The system that we'll consider is puck 1 plus puck 2. Those are the two objects in our system. And we showed that there is overall no external force acting on the system, which means momentum is conserved. That's how we know we can use conservation of momentum. And the way we typically write this is P initial is equal to P final. So the total momentum of the two pucks in this initial state before they collide is the same as the total momentum in this state after they collide. So you can use different notation. What I like to use is primed velocities to equal final velocities. So in other words, for my initial momentum, I'm going to have m1 times v1 for the momentum of the first puck, plus m2 times v2 for the momentum of the second puck. But then in the final state, I'm going to write this as m1 v1 prime, so that's my final velocity for puck number 1, plus m2 v2 prime, right? So that's how I'll differentiate between final and initial with a little prime symbol. Well, we can actually simplify this even more because m1 v1, the initial momentum of puck number 1, should be 0. Puck 1 starts at rest. So it doesn't have any initial momentum. What we're trying to do is figure out v1 prime. We want to know the velocity of puck number 1 after collision. So we'll solve for that by first saying m1 v1 prime is equal to m2 v2 minus m2 v2 prime, just to rearrange that. And then divide by m1 to say v1 prime is equal to m2 divided by m1 times v2 minus m2 divided by m1 times v2 prime. Okay, what I'm going to do is draw a little set of coordinate axes, x, y, just so we're clear. Everything is moving in the x direction. Nothing is moving in the y direction. So this is pretty simple to calculate. What we have is, I can take the ratio of m2 divided by m1 as just a factor out front. So we have 35.0 grams for m2 and 45.0 grams for m1. That was just stated in the problem. And then alongside that, we have v2 minus v2 prime. So again, this is v2 over here, the initial velocity of the second puck. I need to write this as a vector, so it's 2.45 meters per second I hat. That indicates that it's only moving in the x direction. Now this is v2 prime over here, final velocity of that puck. I'm subtracting that, and that's 1.05 meters per second I hat. So what do we get? You compute those, you compute that, and you get 1.088 meters per second, because grams cancel, you're just left with meters per second. Also, the I hat unit vector comes along for the ride, and we'll want to round that to 3 sig figs, okay? So in other words, puck number 1 ends up moving to the right. That's what this I hat indicates, at a speed of 1.09 meters per second. Okay, so this would be 1.09 meters per second. That's how this works. Okay, so I'd like to take a look at another example closely related to what we just did, but slightly more complicated. So rather than all of the motion happening just in a line along the x-axis, this is going to involve motion in 2 dimensions. Okay, so just like before, we have puck number 2 coming in towards puck number 1, and they eventually collide, but instead of colliding head on, puck number 2 is going to hit puck number 1 kind of on the side. Okay, so then after they collide, puck number 1 moves off like this, puck number 2 moves off like this. Okay, so we have the same 2 pucks from the previous problem. Initially, puck number 1 is at rest, puck number 2 is moving towards it at 2.45 meters per second. After the collision, puck number 2 moves at a speed of 1.05 meters per second at an angle of 25 degrees below this horizontal line, as we see here. So what is the speed of puck number 1 after the collision? That's what we want to know. And also, what direction is it moving in? What direction is that arrow pointing in? So let's work this out. Okay, so let's actually start by labeling some of the velocities that are going to come into the equations we write down. So again, before collision, we'll just write these as V2 for puck number 2 and V1 for puck number 1. After collision, we'll put a little prime on there to denote that we're talking about final velocities. So V1 prime is over here, V2 prime is over here. Now, there's a lot we can take away from the previous example. For one thing, we showed that the momentum is conserved, so the total momentum of the 2 pucks is conserved. And from that, we worked out this result that V1 prime, which is still the velocity we're trying to solve for, is equal to m2 over m1 times v2 minus v2 prime. So again, I'm just bringing in the previous work we did. It would be the exact same steps that we took to get here. But now, this is where things change a bit. I'm trying to calculate v1 prime, and I have the ratio of the 2 masses out front, but in the parentheses, I have the difference between these 2 velocities. Now, the thing is, we're not dealing with 1 dimension of motion anymore. We're dealing with 2 dimensions. So in other words, if this is my x-axis pointing to the right, and this is my y-axis, I have to account for x and y motion. So the way I'm going to do this is I'm going to write down m2 divided by m1, which again is 35.0 grams divided by 45.0 grams. And then I'm going to write v2. Okay, so the initial velocity of puck 2. Well, that's 2.45 meters per second. I hat to indicate it's moving in the x direction. And you can also, just as a placeholder, say 0 j hat. There's no motion in the y direction. But then we want to subtract from that the ratio of the 2 masses, once again, 35.0 grams over 45.0 grams. And now I have to write v2 prime, and that one has x and y components. So I have to think about both of those. Well, to get the x component of a velocity, you take the magnitude, which is 1.05 meters per second, and then if I take cosine of the angle, then I'll get the x component. But actually, we should consider this angle to be negative because it's below the x-axis. So I'm going to write this as minus 25 degrees times I hat. Okay, so that's the x component of that second puck's final velocity. The y component would just be 1.05 meters per second sine of negative 25 degrees, and I'll put the j hat unit vector next to that. This is the calculation we have to do to get v1 prime. Okay, so here's what we have. We get an x component as a result of this, and we get a y component. For the x component, well, just look at, I'm going to circle this column right here. So I'm going to have 35 over 45 times 2.45 minus 35 over 45 times 1.05 times cosine of negative 25 degrees. So we just combine the x components, do that big calculation, you'll find it comes out to 1.165 meters per second, and we keep 3 sig figs. Now you do the same exact thing with the y components, but this is much easier because you just have 0 minus 35 over 45, and then times 1.05 times sine of negative 25 degrees. And this works out to 0.3451 meters per second. So to be clear, this is the x component for v1 prime. This is the y component. So what we want is the speed and the direction of that first puck. So the magnitude of v1 prime would be, it's the Pythagorean theorem, we'd take 1.165, the x component, we'd square that, plus 0.345, the y component, square that. That's how we get the magnitude, or the speed. And what does this work out to? 1.215 meters per second, which you'd want to round to 1.22 meters per second. So that's how fast this, the first puck is moving after collision. That's what we calculated using conservation of momentum. Okay, what about the angle? So here, the angle that this puck is moving at is given by the inverse tangent of the y component over the x component. That's generally speaking how you calculate the angle for any vector. So the y component is 0.345 meters per second, and the x component is 1.165. So the inverse tangent of that, if you work it out, is 16.5 degrees. So puck number 1 is moving off at an angle of 16.5 degrees. That would be this angle right here. So we found the two answers we're looking for. Okay, so as a follow-up to those two examples we just looked at, I want you to think about what would happen if these two hockey pucks collided on a tilted table as opposed to one that was completely flat and level. So in this case, okay, if the two pucks are colliding on a tilted table, would we still be able to say that the total momentum is conserved? So try to think of what the answer is. Is momentum still conserved in this case? Yes or no? But also try to think of the reason why, okay? So pause the video, see if you can come up with an answer to this, and then come back to it. Okay, so let's think about it by looking at the forces acting on these two pucks. So now, each one, of course, has a force of gravity or a weight acting on it. So this is the weight of puck number 2. what this shows us is the force that puck number 1 is exerting on puck number 2 when they collide. So I'm going to call that F12. We also have a normal force that the table exerts on puck number 2. But again, this normal force is perpendicular to the surface of the table. So it's not just in the opposite direction as the weight anymore. It's tilted a bit. Also, if we look at the forces acting on puck number 1, we have the force of gravity, or the weight, pulling that one straight down. We also have the force that puck number 2 exerts on puck number 1, okay, which would just be in this direction, down the ramp. And then we have the normal force that the table exerts on puck number 1. So those are the forces we need to think about when it comes to this system of 2 pucks. Now, before, what we showed is the total outside force is equal to 0 when the table is flat. But now that the table is tilted, I don't think that's going to be the case anymore, because if we define the system to be those 2 pucks, the total outside force is going to be this normal force, plus this weight, plus this weight, okay? And of course, these 2 forces are internal, so they don't count in our external forces. All right, well, if I add this normal force to this weight, they actually don't cancel out because they're not going in opposite directions. And when I add this normal force to this weight, they don't cancel out either because they're not going in opposite directions. So the total external force is not 0 anymore. In fact, if you work it out, you can see that there is a net force going down the ramp this way. So since the total external force acting on the system is not 0, momentum isn't conserved. In other words, these 2 pucks, even if they collide, are going to increase in momentum as they move down this way. So we don't want to say momentum is conserved in this case. That would not be true. All right, so let's get into, so there's one topic that I want to touch on really quick at the end of this video, which is elastic and inelastic collisions. So turns out there are different types of collisions that we need to be aware of, and we need to know the difference between them. And I'm going to introduce this topic by way of an example. Okay, so I want you to try this calculation out for yourself. We have a 120 kilogram linebacker running towards an 85 kilogram quarterback who is initially at rest. So the linebacker is running at a speed of 6.5 meters per second towards the quarterback. Okay, so the linebacker tackles the quarterback, so you can consider that tackle to be a head-on collision between the 2 football players. And immediately after this collision, the linebacker and the quarterback are moving together with a common speed. They're just flying through the air together with the same speed. So what is that final speed going to be? And then try calculating this. What percentage of the initial kinetic energy of the linebacker is lost during this collision? And finally, what are some other forms of energy that this lost kinetic energy might have been converted to during the collision? Okay, so here's what I want you to do. Try to draw a picture of this tackle that's going on. Calculate the final speed of the 2 football players as they move off after the tackle. And then calculate the kinetic energy before and after the tackle. And then you can tell me if there's any sort of change. Okay, what percent change are we seeing? So try to work this out. Pause the video, see what you get, and then we'll go through it together. Okay, so the best thing you can do to start off is to draw a picture. We have a linebacker, L, and a quarterback, Q. So before the tackle, this is what everything looks like. This is our initial state. The linebacker is moving towards the quarterback, but the quarterback is standing still. So we'll call that velocity V. Okay, after the tackle, what we have is the linebacker and the quarterback moving together. They're sort of flying through the air now with the same speed. They're moving together, so they have the same speed, they have the same velocity. We'll call that V prime. So this would be the final state. So to figure out what that final velocity is, we're going to use conservation of momentum. And the initial momentum equaling the final momentum is how we'll build the equation. So P initial is P final. Well, what's P initial? We have the mass of the linebacker times velocity V, but then there's no momentum for the quarterback, so I could just say plus 0. On the other side of the equation for P final, it's actually helpful to just think of the linebacker and the quarterback as one big object flying through the air with a combined mass of ml plus mq, and then the velocity being v prime. Okay, so that's how I can apply conservation of momentum here. So then v prime is going to be ml divided by ml plus mq times v prime. And if I just, times v, I should say. And if I want to know just the magnitude of v prime, just the speed, this is how this will work out. We'll have ml, the mass of the linebacker on top, 120 kilograms, divided by the combined mass, 120 plus 85 kilograms for the linebacker and the quarterback on the bottom. And then this initial speed of the linebacker was 6.5 meters per second, like that. So anyway, I'm just plugging everything in here. And when you do this, you get 3.804 meters per second, but we'd want to round that off to just 2 sig figs to make it 3.8 meters per second. So that's how fast they're moving off at the end. That's our final speed. Okay, so again, if we look at these initial and final states, we don't have to just calculate speed, we can also calculate kinetic energy. So we can look at the initial kinetic energy. Well, if we call this, let's just call that K, okay? Only the linebacker is moving, and kinetic energy is given by 1/2 mv squared. So I'm only using the mass of the linebacker. That's the only thing that's moving. The quarterback has no kinetic energy, not moving, so we can just say plus 0. So we have 1/2 times 120 kilograms, and then 6.5 meters per second as the speed, which we'll square, which works out to 2,535 joules if you calculate that. But again, we're going to keep 2 sig figs. Okay, the final kinetic energy. So what's the final kinetic energy of these two football players when we add them together? Let's call that K prime. And again, you could just think of the linebacker and the quarterback as just one big mass. So 1/2 times ml plus mq, that's just the combined mass that's moving. And then the speed is v prime, so I'll say v prime squared. So what I have is 1/2 times 120 kilograms plus 85 kilograms, multiplying 3.804, but keeping 2 sig figs, meters per second, and squaring that. So here's what you'll find. This only works out to 1,483 joules. So kinetic energy has been lost in this collision, has decreased. So how much? How much did it decrease? Well, the percent change you can think of as K final minus K initial divided by K initial, so that's sort of our baseline, times 100. That's how you calculate a percent change. So again, K final is 1,483 joules. K initial, 2,535 joules, divided by K initial, 2,535 joules multiplied by 100. So this actually comes out to something negative, minus 41.49%, or about minus 41%. The negative sign, again, just means we lost energy. Okay, so in other words, even though momentum is conserved, kinetic energy isn't. There's less kinetic energy in these two objects after the tackle than before. So the question then becomes, where did this lost energy go, right? Energy is conserved. So if we have less kinetic energy at the end of the tackle compared to the beginning, it's not like that energy disappeared. It had to go somewhere, right? It had to be transformed into some other type of energy. So where did the energy go? Where did the lost kinetic energy, say, go? Well, it could have gone a number of places. Let's think about it. You might have generated some heat in this collision. That involves energy. You might have produced sound. Imagine two helmets slamming against each other, making a sound. There's energy in those sound waves. Okay, that's one place the energy can go. You can break things. You can break helmets, bones, or at least deform them somewhat, if not breaking them. And that takes energy too. Okay, so these are a number of different ways we could have taken that kinetic energy and converted it to other forms, but something like this must be happening. Okay, so that brings us to different types of collisions. The idea here is that the final outcome of any collision is going to depend on how much kinetic energy the colliding objects will lose during the collision, if any. And we can basically put things in two broad categories, elastic or inelastic. If we have an elastic collision, this means the total mechanical energy of the objects is the same before and after the collision. So delta E, for those two objects, the change in mechanical energy is equal to 0. So it's just the same before and after collision. That would be elastic. An inelastic collision would mean the objects lose some of their mechanical energy during the collision, however much that might be. So delta E, the change in mechanical energy, is something negative, indicating a loss. Now, if you remember, if you think back to chapter 8, this means that if we're losing mechanical energy, there must be some kind of non-conservative force acting on the colliding objects. In other words, the forces involved in the collision when the objects slam into each other are non-conservative in some sense. But here's the thing. The big picture is energy on the whole, if you really account for all types of energy that exist out there, that's something that's conserved, okay? So if you lose mechanical energy, okay, the colliding objects are moving slower after they collide than when they started. That means some of that mechanical energy has been converted to other types of energy. It doesn't just disappear, it's converted to other types of energy. And we mentioned some of these already, things like heat being generated, and sound, and other things like this. So that's the difference I wanted to outline between elastic and inelastic. Okay, so to make this a little bit more clear, to give you something to picture in your mind, I want to show you two examples. So we have an animation of an elastic collision, and we have an animation of an inelastic collision. For the elastic collision over here, what I'm going to show you is a slow motion video of a golf ball approaching a wall and then bouncing back, okay? And this is pretty close to elastic because the ball is moving almost the same speed when it bounces back as when it comes in. So this is what that looks like. See it again? So notice how the ball is deforming a lot when it's actually hitting the wall. And also, while it's pressed up against the wall, it's momentarily at rest. It's not really moving. So what's happening is we have some initial kinetic energy of this moving ball coming in, but it's temporarily converted to elastic potential energy as the ball squishes, kind of like a spring. But then that elastic potential energy is released. It's turned back into kinetic energy as the ball bounces back. So the point is, if we just look at before and after the collision, the ball has pretty much the same kinetic energy before and after. On the other hand, this is an example of an inelastic collision. Two cars collide head-on. And of course, we see that after the collision, there's much less kinetic energy than what we started with. In fact, if you set it up just right, all of the kinetic energy can be lost in the collision. So that initial mechanical energy of the two moving cars has been converted into things like generating heat, making loud noises and deforming the objects. The fact that the frames of these cars are deformed and glass is breaking, again, that takes energy. Where's that energy coming from? It's coming from the initial kinetic energy they had when they approached each other. So actually, one thing just to note, I'm not going to prove this, but you can get the maximum loss of mechanical energy when the objects stick together after collision, which is what's happening in this video, where they stick together afterwards. Okay, so that's it for this video. There's a lot to think about, but we'll end it here, and I'll see you in the next one. Until then, take care. See you later.